Hi, my name is Arnold Rangakoramia. This is Kisembo Academy, and in today's session, I'm going to answer 8 questions. So I'll be taking you through one by one, the working and the answer. These questions were sent to me via email by one of my viewers called Adoba Brown from Ghana. Adoba Brown, thank you very much for these questions. They were really nice ones. And so here I get started with the answers. So here goes the first question. The mass of a piece of cork is 20 grams. What fraction of the cork is immersed when it floats in water? Given the density of the cork is 0.25 grams per centimeters cubed. Now, when we are dealing with these kinds of questions, there are certain things that need to be at your fingertips. We have such a thing we called the law of flotation. We have the law of flotation. Then we also have Archimedes Principle. Now, as I do these questions, my assumption is that you have a clear understanding of the law of flotation and Archimedes Principle, because it is these principles that we are going to use when interpreting these questions. So just a recap, the law of flotation simply says that when a body is floating in any liquid or in any fluid, it will displace its own weight of fluid. And then, of course, Archimedes' principle states that when a body is wholly or partially immersed in a fluid, it will experience an upthrust, and this upthrust is equivalent to the weight of the fluid displaced. So as we are doing these 8 numbers, we will be quoting these laws, and as we quote those laws, we will be able to interpret the questions in this session correctly. So let's get started with this one. The mass of a piece of cork is 20 grams. What fraction of the cork is immersed when it floats in water, given the density of the cork to be 0.25 grams per centimeters cubed? Sometimes I like to interpret my questions using diagrams. So let's try and give a diagrammatic view of this whole thing. This question here, we are having this this is water here, okay, and this is the piece of cork. Now the question says that this piece of cork it's floating, they're saying it floats in water. So meaning that when it floats in water, they are saying that the mass of piece of cork, which is 20 grams, of course this is 20 grams, it is having 20 grams, that is its mass, and its density is 0.25 grams per centimeters cubed. So the mass of a piece of cork is 20 grams, as you can see. What fraction of the cork is immersed in water? So there is this fraction of the cork. What fraction of the cork is immersed in water? And of course, given that density. So now, this fraction that is immersed in water, is equivalent to the portion of the water that has been displaced, if you may think about it. This portion of the cork that is floating, that is underwater, this portion is equivalent to the amount of water that has been displaced. So now what do we know? We know that according to the law of flotation, we know that any floating body will displace its own weight of fluid. So it means that this volume of water, or this part of the cork that is in water, is equivalent to the amount of water that has been displaced, and this amount of water that has been displaced is equivalent to the weight of the cork, because this law says that any floating body will displace its own weight of fluid. So the weight of fluid displaced is equal to the weight of this entire cork. Now I'm trying to go all that way just to, as you face these kinds of questions, you're supposed to take advantage of any kind of information that is disposed or that you may know. So now they're asking, let's get to the real question. What fraction of the cork is immersed? This is the fraction of the cork that is immersed. Now you realize that the fraction of the cork that is immersed is equivalent to the fraction, or the volume of displacement is equivalent to the volume of just that piece that is immersed. So in other words, if you want to find the fraction of the cork that is immersed, the fraction of the cork immersed is going to be equal to the volume of the part that is immersed. Let me call it volume of the cork immersed. Divide that by the volume of the whole cork. So the volume of the cork immersed, divide that by the volume of the whole cork. So once we get these two values, then we are able to get the fraction, what fraction of the cork is immersed. So we shall go, and this is our end product. So we shall go and tackle one by one. So for starters, we know that the volume of the cork immersed is just this portion here down, like we have shaded in red right there. So to be able to get that volume of the cork that has been immersed, this volume that has been immersed is the same as the volume of the water that has been displaced. So how can we get the volume of the water that has been displaced? In other words, if we get the volume of the water that has been displaced, that volume is equivalent to the volume of the cork that has been immersed. So we use the law of flotation to get a relation there. Now we know that the law of flotation states that because the weight of the fluid displaced is equivalent to the weight of the cork. So we know that weight of the fluid displaced is given by mass of the fluid. In this case, this is water, right? So the mass of the water, multiply that by gravity, is given by the weight of the cork, which is going to give us mass of the cork, multiply that by gravity. Okay, so what is mass? If we are to do some side work here, we know that density is equal to mass over volume. If we are to make mass the subject of the formula, it means mass is equal to density times volume. So here in the place of mass of water, since we do not have direct figures for that, we know mass for water is given by, this is going to be the density of the water, multiply that by the volume of the water, then multiply that by gravity, is going to be equal to the mass of the cork. Again, the mass of the cork is going to be given by the density of the cork, divide that by the volume of the cork, multiply that by the gravity, like that. Now, by doing all this, what are we trying to look for? Remember, we're trying to look for the volume of the cork that has been immersed. And now if you look at our expression, here we have the weight of the fluid displaced, and the fluid displaced, that is the volume of the water that has been displaced, or the water that has been displaced. Now the volume of the water that has been displaced is the same as the volume that has been immersed. I hope you're able to get that logically. So the volume of the water that has been displaced is the same as the volume of this portion that has been immersed right there. So by getting the volume of the water displaced, you have the volume of the portion of the cork that is immersed, which is what we are looking for up here. So we make VW the subject of the formula right there. And so we shall say volume of the water displaced is given by, we have here density of the cork, multiply that by the volume of the cork, multiply that by gravity. Of course, when these ones, this is multiply that by, let me write this thing in full first. This is key. This is density of the water. So divide both sides by density of the water times gravity. Divide both sides by density of water times gravity, so that this goes with that and this gravity goes with that. So we shall remain with volume of water giving us density of the cork, multiply that by volume of the cork, multiply that by gravity, divide that by density of the water, multiply that by the gravity. So you realize that the gravity and the gravity there will cancel. You remain with density of the cork. Is it given? Yeah. So we can go ahead and find that to be density of the cork. Now, of course, the density of the cork has been given in our question, but you do not have the volume of the cork. It's not given in our question. Divide that by the volume of the water. But I think it was also not necessary for us to go ahead and expand this. This is the same as, this is mass, remember? that mass is given by density times volume. So it was not necessary for us to go ahead up here and expand this from here to this. We already have the mass of the cork according to our question. We've been given that the mass is 20 grams right there. So even if we didn't expand this, density times this is given, this is mass of the cork. So this is the same as saying mass of the cork, which is 20 grams, divide that by the density of water. So now the density of water, it is either, remember, density of water is either 1,000 kilograms per meters cubed, or it is 1 gram per centimeter cubed. So either of these two. So since our mass is in grams, let's use this 1 gram per cc. So it's going to become 1 gram per cc. And so we shall end up with our volume of the water. Our volume of the water will be 20 centimeters cubed. Our answer here is in centimeters cubed. Of course, the other way you could do it is still, or if you wanted to use a density of water as 1,000 kilograms per meters cubed, it would mean that this 20 grams was supposed to be converted to kilograms so that the units are harmonious. Now for density of water, which is 1,000 kilograms per meters cubed or 1 gram per centimeters cubed, these ones are they are known constants. And when it comes to examination purposes, they are always given to you in your question paper. So that's the volume of water. And if you are to go back up here, remember the volume of the portion immersed, this is the same as the volume of water. So we've gotten the upper part. Now we need to go ahead and find the volume of the cork itself. That is the entire cork. So to find the volume of the cork, we shall go ahead and say we know that density of the cork is given by mass of the cork divided by that by volume of the cork. Now we're interested in the volume. So to make VC the subject of the formula, volume of the cork is given by mass of the cork, divide that by density of the cork. So this is going to become, now the mass of the cork, according to our question, remember our mass is 20 grams. So I shall come here and say this is 20 grams. Divide that by the density of the cork. Is it given in the question? Yes, the density of the cork is 0.25 grams per centimeters cubed. So I'll come here and say divide that by 0.25 grams per centimeters cubed. So the answer we get here for the volume, remember the units have to be harmonious. Mass is in grams, so our density will be in grams per cc. So it means that our answer of a volume will be in centimeters cubed. However, you can as well change those into kilograms. It means you're supposed to change those 20 grams to kilograms. Then you change your density down here to kilograms per meters cubed. You should be able to get the same answers. So what we end up here is 80 centimeters cubed. So we have the volume of the entire cork and the volume of water. So to answer the question here, our question here says that what fraction of the cork is immersed? What fraction? And we say that the fraction is given by the volume of the cork immersed divided by the volume of the entire cork. So if I'm to rewrite here, meaning the fraction. Remember we said that the volume of the cork immersed is the same as the volume of the water displaced. Now remember we're able to, I need to emphasize this. Remember that the volume of the cork immersed and the volume of the water that are displaced are the same, and we're able to get that relation by quoting or by interpreting the law of flotation. Okay, so what is the volume of the water displaced? We got that one up here. We got the volume of the water displaced as 20 centimeters cubed. So I shall come down here and say, so this is going to be 20 centimeters cubed. That's the volume of the water that was displaced, which is equivalent to the volume of the cork immersed. Divide that by the volume of the entire cork. Now the volume of the entire cork, we got it up here as 80 centimeters cubed. So I shall come here and say this is out of 80 centimeters cubed. And so the answer we get here, this is once, that is 4 times. Of course, the centimeters cubed and that centimeters cubed will cancel. We'll end up with a quarter, like that. So that's the answer. We have answered the fraction. The question asked, what fraction of the cork is immersed when it floats in water? And the fraction that is immersed is a quarter. So a quarter of the cork is immersed when it floats in water, and that there goes number 1. Let's move on to number 2. Next number, a beaker weighs 0.4 newtons when empty and 1.4 newtons when filled with water. What does it weigh when filled with brine of density 1.2 grams per centimeters cubed? Again, I like to summarize my questions using small little diagrams like this. So here as we go, we have a beaker weighing 0.4 newtons. So the weight of this beaker is 0.4 newtons. Okay, when it is empty. Here it is empty. And 1.4 newtons when filled with water. So we come here, when this thing is filled with water, the weight of the beaker plus the weight of the water is 1.4 newtons. So here is when it is filled with water. Okay, we get that. And then again, when filled, what does it weigh when filled with brine of density that? So first of all, before we go to the brine, we're able to extract some extra information here. If the weight of the beaker plus the weight of the water is going to give us 1.4 newtons, therefore we can actually go ahead and find the weight of the water itself. To get the weight of the water itself, it's going to be the 1.4 minus the weight of the beaker when it is empty. So 1.4 minus 0.4 gives us 1 newton. So 1 newton is the weight of the water. Okay, so now let's go and find what does it weigh when it is filled with brine of density 1.2 grams per cc. So let's do that right there. So here we have brine. They are asking us to find the weight. What is the weight when it is filled with brine? So here we want the weight of the beaker plus the weight of the brine. What is this? This is what the question is asking. What does it weigh when it is filled with brine of density that? Now, of course, here, this is what the question wants. So in other words, as far as this question is concerned, we are interested in finding this answer right there. Okay, so let's get started with the question. First of all, weight of the brine. Weight of the beaker. We already have the weight of the beaker here. It is 0.4 right there. So if that's the weight of the beaker, it means as far as this is concerned, the weight of the beaker is sorted. Now, we need to find the weight of the brine. That's what we need to find. Now, the weight of the brine, the information about brine is, brine has the density of the brine is 1.2 grams per centimeters cubed. All right, so let's go ahead and find. We should go ahead and find the weight of the brine. So we all know that weight, is given by mass times gravity. Acceleration due to gravity, right? And of course, our acceleration due to gravity for this video shall be 10. That's what we shall use. So what is weight? So we are looking for weight of brine. So the weight of brine is given by the mass of the brine, multiply that by acceleration due to gravity. So do we know the mass of the brine? Of course, the mass of the brine is not given in the question. Yeah, it's nowhere to be given. But however, according to the question, we have some information here. We have the density of the brine. And remember, we said density. We know that density of the brine is given by, mass of the brine, divide that by volume of the brine. So if we make MBR, mass of the brine, the subject of the formula here, we know that mass of the brine is given by density of brine, multiply that by volume of brine. So that's what we are going to come and do here. We know, continuing with our working, we shall know that the weight of the brine is given by, instead of saying mass of brine, we shall instead put this right there. It's going to be the density of the brine which we already have in the question, multiply that by the volume of the brine, then multiply that by the gravity here. So we proceed. Now here, to get the weight of the brine, we have the density of the brine here, which so happens to be 1.2. So this is 1.2 grams per centimeters cubed. Multiply that by the volume of the brine, which we do not know, volume of the brine. Multiply that by the gravity, which is 10. So we need to find the volume of the brine. It's not directly given to us in the question. So what is the volume of the brine? Let's get back to the question and read it more closely. If you have to look at this question, it shows that they are telling us that a beaker weighs 0.4 newtons when empty and 1.4 newtons when filled with water. So when we fill this beaker with water, that is what it weighs. Then they're asking us, what does it weigh when filled with brine? Do you notice something there? Here it was filled with water, here it is filled with brine. So in other words, we are using at the same beaker, so meaning the volume is the same. So what does that mean? It means that the volume with which water was, the volume that the water occupied in order for this beaker to weigh 1.4 newtons, that is the same volume of brine that was used, because the question says the beaker is filled. So we are assuming here that the beaker is filled to the brim. So the amount of volume that was occupied by the water is the same amount of volume that was occupied by the brine. Now, according to our calculation down here, since we do not have enough information to calculate the volume of the brine directly, then we can go ahead and calculate for the volume of water. If we know the volume of the water, then we know it's the same volume of the brine, since it's the same beaker we are dealing with here. So now let's first look at the information given for water that can help us to find the volume of the water. First of all, we know that the weight of the water right here. We know weight of water. Let me write things down here. Weight of water is given by, I think we can leave this maybe equation 1. Then you can come here and say weight of the water, remember, is 1 Newton right there. We know that density of the water is given by, 1,000 kilograms per meters cubed, or 1 gram per centimeters cubed, depending on the circumstance. Yeah, I think that's what we have. So given the information we have here, we can go ahead and simply start by saying that the weight of the water is given by mass of the water, multiply that by gravity. So what were we interested in? Weight of water, which is 1 Newton, is given by the mass of the water. Now, since we do not have the mass of the water directly, we know that from density is equal to mass over volume. We know mass is density times volume, so mass is given by density of water, multiply that by volume of water, then multiply that by the gravity. Now we're interested in finding the volume of the water, because it's the volume of the water which is the same as the volume of the brine. So we make volume of the water the subject of the formula, which shall end up being volume of the water is going to give us 1 Newton, divide that by the density of the water, multiply that by gravity, which is 10. Let me call it G yet. Now take note, for us to find the volume of the water is going to be equal to, here this is 1 Newton. Divide that by the density of the water. Now the density of the water here is going to be 1,000 kilograms per meters cubed. Multiply that by gravity. Gravity is 10 meters per second. And so the answer we shall get here for the volume of the water is going to simply be 1 over 10,000. Let's leave it in fraction form. So 1 over 10,000, that's the volume of the water. Now the volume of the water is the same as the volume of brine. So we shall simply come here and say substitute in equation 1. Now what is our equation 1? Our equation 1 is this one right here. Okay, so we shall come back here and say that this is going to become 1.2 grams The weight of brine is going to give us still 1.2 grams per cc. Multiply that by volume of brine, multiply that by 10. Now remember that this 10 is meters per second squared. That is the acceleration due to gravity. Now the volume, remember here the volume, if you look at our units here, what is the final unit for volume here? Of course, the final unit for volume here will be meters cubed, right there. How do we come to meters cubed? Let me explain that at the end of the question. So this is going to be 1.2 grams per centimeters cubed. Multiply that by the volume of brine. Remember, we said the volume of brine is the same as the volume of the water. So in this case, it's going to be 1 over 10,000. And this whole thing is in meters cubed. Multiply that by gravity, which is 10 meters per second squared, like that. So to go ahead and find the weight of the brine, now this is in meters per second, this is in meters cubed, and now this is in grams per centimeters cubed. We need to harmonize these units. So since this is in meters cubed and this is meters cubed, then this grams per centimeters cubed should be converted to kilograms per meters cubed. We need to convert this to that, so that here we have the meters cubed, here we have the meters cubed, here we have the meters, so that the units are harmonious. They can, cancel themselves out. And in the end, we are able to get the weight of brine, and our weight of brine should be in newtons. Now, so it's more like side work. We are supposed to convert this 1.2 grams per centimeters cubed to kilograms per meters cubed. Let's do that side work here. We are converting 1.2 grams per centimeters cubed to kilograms per meters cubed. What this means is that we are converting 1.2 grams first to kilograms, then afterwards we shall go ahead and convert this 1 centimeters cubed to meters cubed. After converting the two, then we divide. So let's begin with the first part. The first part is converting 1.2 grams per cc to kilograms. We know that 1 kilogram is equivalent to 1,000 grams. What about 1.2 grams? So 1.2 grams is equivalent to, we put here x. When we cross multiply, we shall end up with 1,000x equal to this 1.2 times 1, which is 1.2 grams. Divide both sides by 1,000, and we shall end up with, this goes with that, this is x, giving us 1.2 over 1,000. Let me first leave it like that, as a fraction like that. Then we have converted 1.2 kilograms to, 1.2 grams to kilograms. So this is in kilograms, like that. Now, next phase is we convert 1 centimeter cubed to meter cubed. You're seeing this here. This is like 1 centimeters cubed to meters cubed. So we are converting first of all to meters. We know that 1 meter is equivalent to 100 centimeters. However, here we are dealing with centimeters cubed to meters cubed. So it means that if I'm to make this cubed, it means that I'm supposed to also do this to the power 3. So 1 meters cubed is going to be equal to, is equivalent to this 100 3 times 3, 100 times 100 times 100, meaning it's 1 with 6 zeros. Then centimeters cubed is centimeters cubed. That's what it means. So meaning 1 meters cubed is a million centimeters cubed. What about, so we are converting 1 centimeters cubed to meters cubed. So what about 1 centimeters cubed? So meaning 1 centimeters cubed, what is it equal to? Because we are converting centimeters cubed to meters cubed. We put there the x. When we cross multiply, we end up with a million x, giving us 1 times 1, which is 1. When I divide both sides by a million, I'll end up with that. I'll end up with my value of x being equal to 1 over a million. And this whole thing is in meters cubed. So we have finished. From what we have seen, we have converted grams to kilograms, then we have converted centimeters to meters. Now we divide the two. We divide the kilogram we've got by the meters. So because we want to convert the thing to kilograms per meters cubed. So in this case, we are simply going to come here and say this is a lot of side work. So we shall say, so meaning these kilograms, we shall say 1.2 over 1,000 kilograms, divide that by, this meter, the meters cubed. So it's 1.2, divide that by that, which is going to be over 1 over a million meters cubed. And of course, this is going to become 1.2 over 1,000 times a million. Divide that by 1. These 3 zeros goes with that. This 1 0, this decimal point moves, that goes, decimal point moves, that 0 goes, decimal point moves. So you end up with 1, 2, 0, 0, and this is in kilograms per meters cubed. So after converting that, we come back here now. All this was side work. So we come back to our original question here. So this next step is going to be equal to, what is 1.2 grams per centimeters cubed? This, we convert that to kilograms per meters cubed. We ended up with this answer here, 1,200. So it's what we put here, 1,200 kilograms per meters cubed. Multiply that by this 1 over 10,000. Multiply that by 10. So the units are harmonious. This is meters cubed, this is meters per second squared. This goes with that, this 0 cancels with that 0, this 0 cancels with that 0, and then this 0 makes this come there. So we shall end up here with 1.2 newtons. Now we know that the weight of brine is 1.2 newtons. So that's the answer. Now we have we come back up here, so meaning that we have gotten the weight of the brine. The weight of the brine is 1.2 newtons. So it means this is how our answer is going to be, therefore, because the question says that what does it weigh when it is filled with brine of density that. So since we found the weight, the answer to that, so let me write the answer directly here. I'll simply come here and say that the total weight we know is going to be the weight of the brine, the weight of the beaker plus the weight of the brine. And we know that the weight of the beaker was already found. We know that it was given in the question as 0.4 newtons. So this is going to be 0.4 newtons plus the weight of the brine. Now the weight of the brine, we got it down here as 1.2. So that's going to become, let's put it here, plus 1.2 newtons. So you will find that the answer is 1.6 newtons. And that's the answer. Well, this number had a lot of corners, but the answer is 1.6 newtons. One thing that I needed to emphasize here in this write-up is the importance of following the units. You should know when you should use kilograms per meters cubed. You should know when you should use grams per centimeters cubed. Because your units are supposed to be harmonious in your calculation. If they are not harmonious, you need to convert the one that is out of harmony so that it is harmonious with the rest. This means that when you're doing these kinds of numbers, you need to have a command on unit conversions, how we convert units. You must be very well conversant with that. And then also, still speaking about units, you look at these newtons. I promised to say how does it come to meters cubed. Now this is 1 newton. Where does the newton come from? Remember, newton comes from when we say weight is equal to mass times gravity. Mass is in kilograms, multiply that by gravity, which is meters per second squared. So 1 kilogram meters per second squared is equivalent to 1 newton. So if I am to see how do we come to meters cubed here, this is going to be, this newton is the same as kilograms meters per second squared. Divide that by, down here we have kilograms meters, that is kilograms per meter cubed. Multiply that by this thing here, which is meters per second squared. So now when we are to sort all this out, this is going to become kilograms meters over second squared. That is what this means. Divide that by kilograms over meter cubed. Multiply that by, this is meters over second squared. This is how this turns out. So this meters cancels with one of these m's here to remain with meter squared. So what we have here kilograms meter divided by second squared, divide that by kilogram, divide that by meter squared, second squared. So this is going to end up being kilogram meter, divide that by second squared, multiply that by the reciprocal of this is meter squared, second squared over kilogram. This second squared and that second squared cancel out, that kilogram and that kilogram cancel out, and you remain with meter and meter squared. So meter times meter squared gives you meters cubed. And so that's how this meters cubed comes to be right there. So I wanted us to see how we end up with meters cubed at that point with velocity of, the water. Now this is essentially how all this works. Now this is a broad topic there's a topic called dimensional analysis. It's for people doing A-level physics. This is how I've recorded it on the channel. This is how these units play out. So again, I emphasize that it's important to know when you should use grams per cc and when you should use kilograms per meters cubed. How do you know that? Just look at the rest of the things you're multiplying things with. For example, here we had meters cubed, multiply that by meters per second cubed. We couldn't multiply that with grams per cc because now this is centimeters and now this is meters. The two are not harmonious. So that's why we had to convert from centimeters to meters cubed, then grams to kilograms, and then we continue with our calculation, and the answer we get here is 1 newton. Again, if you're to look at this, we said that 1 newton is equivalent. Let's try it out here. This is kilograms per meters cubed, so this is kilograms per meter cubed. Multiply that by meters cubed. Multiply that by, we will say kilogram per meter cubed. Multiply that by meters per second squared. Let me put this down here like that. Kilogram per meters cubed. So this meters cubed and that meters cubed cancel out. You remain here with kilogram. Kilogram times meter is kilogram, meter per second squared. And this is the same as saying kilograms meters per second squared. Remember, this is what we got up here. Let me take you back here, up there. Right there. when we were saying that the 1 Newton comes from kilograms meters per second squared, you realize that here it's the same thing. We are having kilograms meters per second squared, and this is equivalent to 1 Newton, and that is why our answer here is in newtons. Well, I was not supposed to go so far into elaborating how the units come about, but I think I just felt it was important to clear this whole units thing right on this very number, because as we move on to the other numbers, we are going to face a lot of this. There are areas where we are supposed to make conversions here, conversions there, and I feel you need to understand where the conversions, why we are doing the conversions and how they are coming about. So that was number 2. We move on to number 3. Number 3, the density of a body is 5 times 10 to the power 3 kilograms per meters cubed, and it weighs 1 Newton in air. Okay, calculate the apparent weight of the body when totally immersed in water. So they're telling us that the density of the water is 1,000 kilograms per meters cubed, and the gravity is 10 meters per second. Now, again, I like to summarize my things using diagram. Let's say this is a spring balance, and on that spring balance we have this body. They are saying that this spring balance will measure 1 Newton when this object is in air. Okay, and the density of this object, let me call it density of the object, is 5 times 10 to the power 3. This is in kilograms per meters cubed, like that. Okay, so what happens is when we put this same object and we immerse it in water, right there, this is the water they are talking about. They are asking us to find the weight. If that's a spring balance, what will be the weight of that when the thing is in water like that, when this body is in water? Here it's in air, here it's in water. So what will be the weight of that body? So that's the question we're supposed to answer. As you can see, calculate the apparent weight of the body when totally immersed in water. So when they want us to find the apparent weight of the weight of the body when it's immersed in water, here they're telling us that when it is totally immersed. So my diagram here should indicate that the thing is totally immersed in water, like that. So it is totally immersed in water. So they want us to find the apparent weight, and this is what they want us to find. The apparent weight, in other words, what will this spring balance read when this body is totally immersed in water? So now this is what is happening here. When it is in air, this is 1 Newtons, right? However, when it is in water, this spring balance will weigh less than 1 Newton. Why is that? It will weigh less than 1 Newton because when you insert this body in water, it's going to experience an upthrust force. That upthrust force is going to make the reading on this spring balance to be less than 1 Newton. So that is one thing to look out for, that in all your calculations, your answer should be less than 1 Newton because of this upthrust force. If I may draw another diagram here, when this body is in water here, this is what is happening. At first, it is experiencing, this is the body, there is a force due to the body acting downwards, that is the weight, and we know that weight to be 1 Newton. However, when the thing gets in water, it's going to experience an opposing force that is going to be pushing it outwards. And that opposing force is what we are calling the buoyant force, or call it the upthrust force. So that upthrust force is acting in the opposite direction. So for us to be able to get the apparent weight of this body, it means it's going to be the weight of the body, or the force moving downwards, minus the upthrust force. So in other words, for us to get the apparent weight, this is what we're supposed to do. The apparent weight of this body is going to be given by the weight of that body in air minus the upthrust force. Sometimes it's called the buoyant force, the upthrust force. So when these forces cancel out, the balance is what is going to be referred to as the apparent weight. So we are going to get started with our calculations. For starters, we already know the weight in air. We know the weight in air, it is 1 Newton. That is already been determined. So now we need to find this upthrust force. This force that is acting down here, that is causing this thing to move upwards. So of course, again, like I had mentioned earlier, you need to have a proper command of these laws, the law of flotation and Archimedes principle. And in this case, since this body is totally immersed in the fluid, it means Archimedes principle will work. And we know that Archimedes principle simply states that when a body is partially or wholly immersed in a fluid, it's going to experience an upthrust force, and this upthrust force is equal to the weight of the fluid that has been displaced. So for us to get this upthrust force, it's equal to the weight of the fluid that has been displaced by this, body. So that's how we are going to solve this. So we shall come here and say upthrust. The upthrust force is given by the weight. Okay, so now what's the weight of the fluid? Of course, we know that weight of the fluid is going to be mass of the fluid times the gravity. So what is the mass of the fluid? Now, according to the information we have the density actually the fluid is water, because it's where it's mass. So we only have the density of water. Do we have the volume? That we know that density is equal to mass over volume. So meaning that if we are to make mass the subject of the formula, we know that mass is equal to the density times the volume. So here the mass here is going to be given by the density times the density of the fluid, multiply that by the volume, occupied by the fluid, multiply that by gravity. So do we have the density of the fluid? Of course, the density of the fluid is water, so the density is 1,000 kilograms per meters cubed. Multiply that by the volume of the fluid. We do not have the volume of the fluid given to us in the question, do we? No, we don't. So we can leave that at that for now. Volume of the fluid, multiply that by gravity, which is 10 meters per second. So we need to find the volume of the fluid that has been displaced. Now, we do not have the volume of the fluid that has been displaced, but we know that the volume of the fluid that has been displaced is the same as the volume of the body that has displaced that fluid. So meaning if we find the volume of the body, it's the same as the volume of the fluid that has been displaced, since this body has been completely immersed in the water. So we shall go ahead and find the volume of the fluid or of the body. So to find the volume of the body, let's first find, we say, but the volume of the fluid is the same as the volume of the body. So what's the volume of the body? The volume of the body, what information do we have to help us find the volume of the body? We already have the density of the body, which is this one. We already have the mass of the body in air, which is that one. So from this information, we can find the volume of the body. From density is equal to mass over volume. We're interested in volume. We know that volume is equal to mass over density. Okay, so it means that here the volume of the body is the mass of the body, divide that by density of the body. So what do we have for mass of the body? So going back to our questions, do we have any information for mass of the body? Yeah, we have, okay, we do not have the mass, but we have the weight. I hope you know the difference, weight and mass. Let's do some side work up here. Weight is equal to mass times gravity. We know that weight, which is 1 Newton, is equal to the mass, multiply that by gravity, which is 10. We're interested in the mass, so we make m the subject of the formula. So divide both sides here by 10, here by 10. We have here, this goes with that, we have our value of m, which is mass, is equal to 1 over 10 kilograms. Okay, because here we have the weight as 1 Newton. So we find the mass corresponding to this weight, which is 1/10 of a kilogram. So that's what we put here. So it means that here our mass is 1 over 10 kilogram. Divide that by The density of the body. Now, if you look up here, the density of the body is given. It's right there, 5 times 10 to the power 3. So this is going to become, divide that by 5 times 10 to the power 3. So yeah, so this is the same, let's say this is divided by 1. So this is going to become 1 over 10 times 1 over 5 times 10 to the power 3, which is the same as saying it is 1 over 5 times 10 to the power 4. And this is the volume. So this is the volume. It is in meters cubed. So this volume is what is going to occupy that. So if I'm to continue this step up here, down here, we shall continue and say that, so meaning this is going to be equal to, 1,000 kilograms per meters cubed. Multiply that by the volume of the fluid, which is the same as the volume of the body that has displaced that fluid, which we have gotten here, which is 1 over 5 times 10 to the power 4. Multiply that by 10. As you can see here, this is meters cubed, and this is meters per second squared. So meaning that the units are harmonious. So we can continue comfortably and say this is 1,000. Multiply that one by 1 over 50,000. Multiply that by 10. These 3 zeros cancel with those 3 zeros. This goes with that. We shall remain with 1 over 5. And 1 over 5 simply means, in decimal point form, this means 0.2. So the upthrust force is 0.2 newtons. So in other words, if I may redraw what I drew up earlier, let me put it here. We have this thing when it is measuring in air, the weight acting downwards is 1 newton. When I put this thing in water like this here, it's going to experience an upthrust force of 0.2 newtons. This is what we've just found here, an upthrust force. So it means that if it is in water, it still has its weight acting downwards, which is 1 newton, but then also it is experiencing an upthrust force acting upwards of 0.2 newtons. So that means that the apparent weight, therefore, is going to be given by its weight in air minus upthrust. Its weight in air is 1 newton. Multiply that, subtract the 0.2 newtons, which is the upthrust force, and you end up with 0.8 newtons. So that gets us to answer the question. The question here they required us to find, to calculate the apparent weight of the body when totally immersed in water. And yeah, we've answered that question. The apparent weight is 0.8 newtons. That's the answer. They're saying a solid of mass 1.3 kilograms suspended by a string is completely in water. If the tension in the spring is 6 newtons, calculate the upthrust of the solid, the volume of the solid, its density, and so forth. Again, let's draw a picture here. We have this solid. Let me draw a circle. It is completely immersed in water. So this is the water in which this solid is completely immersed in, as you can see. Okay, so if that the solid is completely immersed in water, if the tension in the spring is 6 newtons, now this is the string. Now this string, it experiences a tension like that. And we know that the tension in this string is equal to, it's action and reaction, and equal but opposite. If there's a tension acting in that direction, it is equal to the apparent weight of this body when it is immersed in water. Okay, because the forces downwards are equal to the forces upwards. Action and reaction and equal opposite. So the forces downwards so happen to be the apparent weight of this solid when it's in water, and so the reverse force is going to be experienced by that tension force. Okay, let's continue to the question. Calculate, number 1, the upthrust on the solid. So to find the upthrust on this solid, if you look at this question, they're telling us that this solid has a mass of 1.3 kilograms. It has a mass of 1.3 kilograms. Okay, so if it has a mass of 1.3 kilograms, that is its normal mass. So what about its weight? So if the mass is 1.3 kilograms, it means that its weight when it's in air is going to be its mass times gravity. In this case, it's going to be 1.3, multiply that by 10, and that's going to be 13 newtons. So that is its weight when it's in air. So in other words, we have the weight of this body, of this solid when it's in air. Let me call its weight when it's in air, like that. Okay, so if that's its weight when it is in air, now they're telling us that when this is completely in water, or when this solid mass is completely immersed in water, the tension in the string is 6 newtons. If it is 6 newtons, it means that this 6 newtons is equivalent to the weight of this solid when it is completely immersed in water. The weight is equivalent to, the tension. This is what I mean. If this body was not immersed in, it was not immersed in any liquid, it would mean that when it is dangling like that, the upward forces are equal to, the downward forces. And from here, when the upward forces are experienced in that string as the tension, from Newton's third law of motion, that action and reaction are equal but opposite. So in other words, when the thing will be 13 newtons, or in other words, the tension in this string will be equal to 13 newtons when this thing is dangling in air, this ball. Now, when we go ahead and put this ball in water, like you're seeing up there, the tension reduces from 13, it reduces to, 6 newtons. Or in short, the weight, the tension experienced in the string is the same as the weight experienced by this, because the upward forces are equal to the downward forces, and the downward forces are the ones responsible for, the weight. So at first it was 13 newtons when it was dangling in air. Then when we put it in water, it reduces by 6 newtons. Now the question is, why does it reduce from 13 to 6? It's because when we put this ball inside this water, it experienced an upthrust force, and it is that upthrust force that caused this tension to reduce from 13 to 6 newtons. So what is the amount of that upthrust force? That is what they're asking us here. The upthrust on the solid. What's the amount of that upthrust? So we shall say here, number one, that the upthrust is going to be equal to, the weight when the thing was in air minus, we are going to take away the weight when it's up. This tension, this is its apparent weight when it's in water, because it's the tension experienced in the string when it is in water. So its weight when it's air minus the apparent. So this is going to be equal to, weight in air is definitely 13 newtons minus its apparent weight in water. Its apparent weight in water here is 6 newtons. So 13 minus 6 is going to give us 7 newtons. So this is it. This is the upthrust. This is the upthrust that is causing these 13 newtons to reduce to 6 newtons. So number 2, we want to find the volume of the solid. So of course, to find the volume of the solid, that's number 2. Let me use another color here. Number 2, we need to find the volume of the solid. Now the volume of the solid is going to be equal to the volume of the water that has been displaced. So again, we shall use Archimedes principle here. We shall say that that upthrust is given by weight of fluid displaced. Upthrust is given by weight of fluid displaced. We already found the upthrust before as 7 newtons. So 7 newtons, which happens to be the upthrust, is going to be equal to the weight of the fluid displaced, which is the mass of the fluid, multiply that by gravity. And that's going to be equal to, that is 7 newtons is going to be equal to mass of the fluid. Remember, we say density is equal to mass over volume. So when we make mass the subject of the formula, mass is given by density times volume. So this becomes density of the fluid, multiply that by volume of the fluid times gravity. Now remember that the volume of the fluid that has been displaced is the same as the volume of the solid that is displacing. This is the same as the volume of the solid that is displacing. So in other words, shall simply come and say 7 newtons is given by density of the fluid, and of course this is gravity. Remember, the volume of the fluid displaced is the same as the volume of the solid, and this is what we are looking for, Vs. Okay, so it means when we make Vs the subject of the formula, Vs, volume of the solid, is going to be given by 7 newtons. Divide that by density of the fluid, which happens to be water, multiply that by gravity. Okay, so this is going to become 7, divide that by density of the fluid is 1000 because we're dealing with water, multiply that by gravity, which is 10. 37 over 10,000, cancel that 0, decimal point moves there, this goes there, this moves like that, this moves like that, this 0, decimal point moves to there. So what we have here is 0.000. So in other words, our answer here is 0.0007. And this is the volume of the solid, it's in meters cubed. So that's the volume of the solid. So moving on to the third question, they're asking us to find the density of the solid. Of course, this is straightforward. To find the density of the solid, that is part 3, density of the solid is going to be equal to mass of the solid, divide that by the volume of the solid. The mass of the solid has been given in the question. Yes, the mass of the solid was given in the question as 1.3 kilograms right there. So the mass of the solid is 1.3 kilograms, divide that by the volume, which is 0.0007 meters cubed, and we shall end up with so we have here a piece of metal is 3.6 kilograms and it is suspended from a spring balance. What's the reading of the balance in newtons with the metal in air, with the metal in water, with the metal in brine? So what is the density of the liquid in which it gives a reading of 33 newtons? All that. So let's begin with the first one. A piece of metal, the weight of the metal is 3.6 kilograms. A piece of metal 3.6 kilograms is suspended from a spring balance. What is the reading of the balance in newtons with the metal in air? So if it is 3.6 kilograms and that is its mass, so of course its weight in air, of course this is straightforward, weight in air is going to be equal to its mass times its gravity. Its mass is 3.6 kilograms, multiply that by gravity, which so happens to be 10, and of course this is going to be 36 newtons. That is number 1 answered like that. That's its weight in air. Okay, so number 2, what is they're saying what's the reading of the balance in newtons, meaning they want the weight, with the metal in water. Of course, now if the metal is in water, it means it's going to experience a certain upthrust. And so when we subtract that amount of upthrust, we shall be able to find its weight when it is in water. So again, right here we have when the thing is in water, the metal there, this is the metal, it's in water. Okay, so first of all, water has a density of 1000. kilograms per meters cubed. That's the density of water. That's the density of water. Now the density of the metal is 9,000 kilograms per meters cubed. Okay, so we need to find the upthrust this thing is going to experience when it is in water. So let's go on and find that. So upthrust is equal to weight Upthrust is given by weight of fluid displaced. So we know that the weight of the fluid displaced or the weight of the water displaced is given by the mass of the water, multiply that by gravity. The mass of the water mass is given by density of the water, multiply that by volume of the water, multiply that by gravity. So we go ahead, density of water definitely is 1,000. Then we are going to multiply that by the volume of the water. Do we know the volume of the water? Now, of course, we do not know the volume of the water that has been displaced, but we know that what has displaced this water is this metal, the metal right here. So if we find the volume of the metal, then we know the volume of the water that has been displaced. So we do not know that. Let's first put it like that. Volume of the water, multiply that by gravity, which is 10. So we need to first figure this out. We need to first figure out what the volume of the water is. So let's do some side work here. We know that density, now the density of the metal. Density of the metal is given by the mass of the metal, divide that by volume of the metal. We want to find this volume because this volume of the metal is the same as the volume of the water that has been displaced. Okay, all right. So let's make volume of the metal is given by mass of the metal divided by that density of the metal. And of course, this is going to be more like, what's the mass of the metal? The mass of the metal, according to our answers here, the mass of the metal, according to our question, is 3.6 kilograms right there. So we shall come here and say this is 3.6 kilograms, divide that by the density of the metal, which is right there, 9,000 kilograms per meters cubed. So this is 9,000 kilograms per meters cubed. And of course, that is going to give us 0.0004 meters cubed. So that is the volume. Okay. So sometimes I like to leave such answers in fraction form because it's easier to put this right there. Then I continue with my working up here. So let's get back to what we are actually looking for. We are looking for, we are trying to look for the upthrust that is experienced when the thing is dropped in water. So in other words, this is going to become 1,000. Multiply that by the volume of the water, which is this one. It is this figure before we come to that, but this can still work. Let's put it in here because it's easier to deal with it when it is like this. 3.6 divided by 9,000, multiply that by 10. So that's going to be equal to 3 zeros, cancel with those 3 zeros, and then we remain with 3.6 over 9, that is 36 over, by that 0, the decimal point moves to there, it becomes 36, divide that by 9, and that's going to be equal to 4 newtons. Now that we have known that the upthrust is 4 newtons, now remember the question is asking us to find the weight. What is, number 2? What is the reading of the balance in newtons with the metal in water? So in other words here, like you see this diagram here, when this metal here is in water right here, as you can see it's in water, it's going to experience a force acting downwards, which is the weight of the metal when it's in air. Then it's going to experience an upthrust force. So meaning that if we have a spring balance up here, the reading of this spring balance is a resolution of these two forces. It's going to be, since the weight in air is greater, so it's going to be weight in air minus the upthrust for us to be able to get the weight when it's in water. And that is what we call the apparent weight in water. So this is what we mean by when they ask what is the reading of the balance in newtons with the metal in water. So when the metal is in water, we are going to come here and say that the reading of the metal when it's in water is given by the weight when the metal is in air minus the upthrust. Minus the upthrust to give us the weight when the thing is in water, the reading. So the weight when it's in air was already given before, and that was 36 newtons right there. Minus the upthrust, we already got the upthrust as 4 newtons, so minus 4 newtons. So 36 minus 4 is going to give us 32 newtons. So this is the weight or the reading of the metal when it's in water. This is also called the apparent weight in water. So again, they want us to find number 3, they want us to find the reading of the balance in newtons with the metal in brine. So it's going to be the same approach. If the thing is in brine, it means we need to first find the upthrust experienced by the metal when it's in brine. Let me draw something here. This is, the thing. This is now brine. When the metal is in brine, it's going to experience an upthrust. So let's find that first of all, we already know the weight in air, it is 32 newtons. Okay, now we want to find the weight of this thing when it's in brine. We need to first do that by finding the upthrust. So upthrust, this is what we are looking for, is equal to weight of fluid displaced. So that's going to be the mass of brine, because it's in brine, so it's going to be the mass of the brine, multiply that by the gravity. The mass of the brine is going to be given by the density of the brine, multiply that by the volume of the brine. Where are we getting this from? If I may do some quick side work here, density is equal to mass over volume. If we make mass the subject of the formula, mass is given by density times volume. So this density times volume is what is here. Density times volume is giving us the mass of brine. So it's density times volume, multiply that by gravity. So this is going to become, what's the density of brine? We'll come back up here according to our question. The density of brine is 1,200 kilograms per meters cubed. So we shall come down here and say density of brine is 1,200 kilograms per meters cubed. Multiply that by the volume of brine. Now remember, we are dealing with the same metal. It's the same metal that we dipped in water before here, right here. It's this same metal we dipped in water, and it's the same metal we are dipping in brine. So it means that if this same metal was able to displace, this amount, this is the amount that was displaced. This is the volume of the metal. So if that's the volume of the metal, and we say this volume of the metal is the same volume of the water that was displaced, it also means that that same volume, it's going to be the same volume of brine that is displaced. So this is going to become this way. Yes, we can go ahead and put this. Okay, let's put 0.0004 right there. So multiply that by 0.0004. But it is also okay to go ahead and just put this fraction here. You'll still get the same answer. So that's the volume. The volume of the metal, which is 0.0004 meters cubed, is the same volume we shall put here. Multiply that by gravity, which is 10. So that is going to become, of course, this is going to end up being that 0 cancels, that decimal point moves there. That 0 cancels, the decimal point moves up there. This 0 cancels, that decimal point moves there. So we shall end up with 12, multiply that by 0.4, right? So what we have here is 4.8 newtons. So 4.8 newtons so happens to be the upthrust. So if that's the upthrust, so it means that the weight in brine, the weight of the spring balance in brine is going to be given by, it's going to be the weight in air minus the upthrust. The weight in air, we already have that in our question as 32 newtons. Multiply minus the upthrust, which is 4.8 newtons. So 32 minus 4.8 is, I think we made a mistake here. This is not 32 newtons, this is 36 newtons. This weight in air is actually 36 newtons, not 32. That was a mistake. Sorry about that. So it means that this is also supposed to, the weight in air here is also supposed to be 36 newtons. So 36 newtons minus 4.8 is going to give us, so 31.2 newtons is the weight of the metal in brine. Alright, let's go on to number 4. So number 4 is requiring us here, as you can see, what is the density of a liquid in which it gives a reading of 33 newtons? So what do they mean by this number 4? What is the density of the liquid in which it gives a reading of 33 newtons? So now let's try and draw a picture to, to summarize this. Let me do it right here. So we have this, we've put in our metal there, and the spring balance here is 33 newtons. So if the spring balance here is 33 newtons, the question is requiring us to find the density of this liquid. What is this liquid that is causing the spring balance to read 33 newtons? So, of course, that is easy to do. So now, first of all, we need to find, we know the weight of this thing in air. Remember, we said that its weight in air is given by, according to the question, it is right there. 3.6 kilograms, or in other words 36 newtons. Okay, so if this is 36 newtons, and now when the thing is dangling in air, its weight in air is 36 newtons. Then when we put it in a certain liquid, we don't know, let's call that liquid L, weight of that liquid L is going to give us 33 newtons. It means it's experiencing a certain upthrust. So what is this upthrust? So let's find this upthrust. Yeah, so to find this upthrust, remember at first it was 36 when it's dangling in air. Then when you put it in brine, its weight reduced to 33. So this weight reduces to 33 because there is certain force acting down here in the opposite direction. Maybe if I'm to redraw this very well, let me draw it down here. This is the metal right there. It is experiencing a force acting downwards. That's the weight in air, which is 36 newtons. But then when I put it in water, it experiences a certain force, which we do not know. Let me call that the upthrust force. We do not know it's the amount of upthrust force, but it causes the overall force here, the resultant force, to be 33 newtons. So it means for me to get this 33 newtons, it was as a result of this weight in air minus upthrust. I'm interested in finding the upthrust. So we know that when this thing was in this unknown liquid, we do not know, it experienced an upthrust. So when I make upthrust the subject of the formula, that's how I come up with upthrust is going to be given by, the weight of the air minus the apparent weight in that liquid, which is the weight when it's in that liquid. So that's going to be weight in air, which is going to be 36 newtons minus the 33 newtons. And then we shall end up with 3 newtons. So 3 newtons is the upthrust force. So now that we have known that this is the upthrust force, then we can simply go ahead and find the density, because the question requires us to find the density. So we shall simply come here and say that upthrust is weight of fluid displaced. The upthrust force we've found is 3 newtons. It's going to give us the weight of fluid displaced, which so happens to be the mass of that fluid times the gravity. When we break down mass, mass is density of that fluid times the volume of that fluid times gravity is going to give us 3 newtons. And what does the question want? If you look at the question here, they want us to find the density right there. Find the density of the liquid in which it gives a reading of 33 newtons. So to go ahead and find the density of that liquid, we shall go ahead and say divide both sides here by volume of the fluid times gravity, divide by volume of the fluid times gravity. This goes with that, this goes with that. We shall remain with the density of the fluid giving us 3, divide that by volume of the fluid, multiply that by gravity. And we all know that this is going to be 3, divide that by the volume of the fluid is the same as the volume of the metal. And we found the volume of the metal before to be 0.0004. So it's the same thing we shall be doing here since we're dealing with the same metal. This is going to be 0.0004. Multiply that by the gravity, which is 10. And of course, that is going to give us the density of the fluid they are looking for, 750 kilograms per meter cubed. Now that answers. Now we've been able to answer all the 4 parts. I think from this you're able to see that when it comes to the weight in air, weight in liquid, upthrust force and whatever, it's not a good thing to just cram those formulas. You need to draw a diagram so that you're able to understand which force is acting at what, and that will enable you to do the number correctly. Proper interpretation leads to proper working, which will give you the correct answer. Next number. A relative density bottle of 25 grams has a capacity of 50 centimeters cubed. The bottle is completely filled with methylated spirit and its mass is 65 grams. The bottle is emptied and some salt is then put into the empty bottle and then weighed. The mass now is 50 grams. Methylated spirit is now added until the bottle is completely filled and the total mass now becomes 80 grams. From the data given, calculate the density of the salt. So let's summarize this using a diagram again. We have a relative density bottle of mass 25 grams. So let's draw that bottle here. That's the relative density bottle right there. So let me say the mass of this bottle is 25 grams. Okay. It has a capacity of 50 centimeters cubed. So the volume of the bottle is 50 centimeters cubed. Okay. The bottle is completely filled with methylated spirit. So I fill this bottle with spirit. Let me call this spirit. When I fill it with spirit, what happens? And they're saying that when I fill it with spirit, its mass is 65 grams. So this means that the mass of the bottle plus the mass of the spirit is not the Holy Spirit, but methylated spirit. The mass is 65 grams. Okay, so the mass of the bottle plus the mass of the spirit is 65 grams. Then they are saying that the bottle is emptied and some salt is then put into the empty bottle and then weighed. The mass is now, 50 grams. So meaning that when I get this bottle and then I put salt, let me put here salt, and I weigh it, it means that the mass now is 50 grams. So this simply means that the mass of the bottle plus the mass of the salt, let me put this spirit SP to not to confuse ourselves. So this is the mass of the bottle plus the mass of the salt is giving us 50 grams, like that. So they're telling us here that the bottle is emptied and some salt is then put into the bottle, the empty bottle, then weighed. The mass is now 50 grams, okay? Methylated spirit is now added until the bottle is completely filled. So after, when the salt is still there, we get that bottle here, and in this bottle now we have salt right there, and then we have the spirit inside that bottle. Okay, and they're telling us that when the methylated spirit is now added, until the bottle is completely filled, the total mass becomes 80 grams. So it means here we have mass of the bottle plus the mass of the spirit plus the mass of the salt. All this is giving us 80 grams. Like that. So that's the interpretation. So they're asking us that from that data given, calculate the density of the salt. Wow. Now, of course, for us to be able to find the density of the salt, we know that density of the salt is given by the mass of the salt, divide that by the volume of the salt. So our task is to find the mass of the salt from the information that has been given to us, and then the volume of the salt from the information that has been given to us. If we are able to find those two, then we are good to go. So let's get started with, data digging. Let's dig the data. So the mass of the salt. So looking at these, the salt comes in at this level. Remember here we already have the mass of the bottle right here. It is 25 grams, right? And then here the mass of the bottle, which we already know as 25 grams, plus the mass of the salt is giving us 50 grams. So from this equation here, we're able to see the mass of the salt. We know, let me do it here like this. We know that mass of the bottle plus mass of the salt is equal to 50 grams. We know that the mass of the bottle is 25 grams. How are we able to know that? We're able to know that from this information here. At the beginning, when the bottle was empty, they told us the mass was 25 grams. So it's 25 plus mass of the salt is equal to 50 grams when the two are added. So when we make mass of the salt the subject of the formula, it's going to be 50 grams minus 25 grams, and we shall end up with 25 grams. So in other words, as far as the mass of the salt is concerned, it has already been sorted. Okay, the mass of the salt is 25 grams. Okay, now that we have the mass of the salt, it is 25 grams. Now what about the volume of the salt? Let's not forget that the volume of this thing we are using, first of all, the volume is 50 centimeters cubed. So in everything that is going through here, we are dealing with the same bottle, density bottle, which is 50 centimeters cubed. That's the volume. Now we want to find the volume of the salt. From that, we can analyze this using, the volume of the spirit. Because look at this final thing. Here we have the salt, the spirit, and the salt and the spirit are mixed together in this bottle. Now, the salt and the spirit here are mixed together to make 50 centimeters cubed. But from this, we can look at, we know that here at first, the spirit was here, it occupied this entire bottle on its own. Okay? And so now we need to ask ourselves, what was the mass of the spirit here? Right there. What was the mass of the spirit that occupied 50 centimeters cubed? So we can go ahead and ask and say, first of all, remember that the mass of the bottle here is 25 grams. So we can find the mass of the spirit. We know that the mass of the bottle plus the mass of the spirit, when together they gave us 65 grams. The mass of the bottle, we know it as 25 grams, plus the mass of the spirit gave us 65 grams. When we make the mass of the spirit the subject of the formula, we shall end up with 65 minus 25. And that is going to be equal to 65 minus 25 is going to give us 40 grams. So what does that mean? It means that right here, when the spirit was completely filled here, it was 40 grams. So in other words, 40 grams of this spirit occupied 50 centimeters cubed. So we can note that down here on the side, and we shall say that 40 grams of spirit, 40 grams of spirit occupied how much? It occupied 50 centimeters cubed. So if 40 grams of spirit occupied 50 centimeters cubed, what about here? How much volume is occupying here? Remember, in this instance here, we have both the salt and the spirit. Both of these two combined occupy 50 centimeters cubed. And we say that the mass of the bottle plus the mass of the spirit plus the mass of the salt give us 80 grams. So in this case, we need to find what mass of spirit is occupying in this third instance. We know that the mass of the bottle is 25 grams plus, now we do not know the mass of the spirit, because remember we simply added here salt, and the salt we added, we know the salt, we got the salt here as 25 grams, right? So when we added salt here, 25 grams of salt, we simply added this methylated spirit. So this 25 grams of salt is what is here, 25 grams of salt plus, now the mass of the spirit, let's call it X, is equal to 80 grams. So this mass of the spirit, why should I call it X? Let me just call it M, mass of the spirit. So this is going to be 25 plus 25, which is 50 grams, plus mass of the spirit is going to give us 80 grams. So here mass of the spirit is going to give us 80 minus 50, which is going to give us, mass of the spirit is going to give us 80 minus 50, which is 30 grams. So it means that let's move slowly, right? At first here we put 40 grams in this right here, and this 40 grams filled up the entire density bottle, and the volume it occupied was 50 centimeters cubed. Then afterwards we emptied this bottle, we put in salt. When we put in salt, in this case, while the salt was still there, we filled this bottle with spirit. Of course, when we add this bottle with spirit, it can't be the same amount of spirit like before here, because right here there was no salt, and when there was no salt, the 50 centimeters cubed of this, the entire volume of this density bottle was occupied by 40 grams. But now when there is salt, we realize that when we added it with spirit, it only took up 30 grams right there. So if we have 30 grams of spirit here, we need to find out what volume do these 30 grams occupy. Then it is from then that we shall be able to know the volume that is occupied by the salt, because remember, we are interested in finding the volume of the salt so that we're able to find the density of the salt. So from here, we have our analogy here that 40 grams of spirit occupy 50 centimeters cubed of the density bottle. That is what we got in our second diagram here. So what about these 30 grams that we've now these 30 grams here, what about 30 grams of spirit? How much volume shall they occupy? That's the value of X. We cross multiply. When we cross multiply, we end up with 40X being equal to 30 times 50. So that is going to give us, 40X, our value of X is going to give us 30 times 50. Divide that by 40. This goes with that by 2. Here we have twice by 2, 15. So we shall end up with So we've ended up with 37.5. So 37.5 centimeters cubed. So 37.5 centimeters cubed is the volume that has been occupied by the spirit. So if I may redraw this here, down here, remember we have this density bottle. Its total volume is 50 centimeters cubed. Let me put it there like that. Its total volume is 50 centimeters cubed. But here there is salt and there is spirit. We realized that, the spirit right now is occupying 37.5 centimeters cubed. That's what we've been calculating. So if the spirit is occupying 37.5 centimeters cubed, then we can find what is occupied by the salt, because what is occupied by the salt plus what is occupied by the spirit should give us the total volume of the relative density of bottle, which is 50 centimeters cubed. So volume occupied by the salt is given by, it's going to be 50 centimeters cubed minus 37.5. And what do we have? It's going to give us 12.5 centimeters cubed. So 12.5 centimeters cubed so happens to be the volume that is occupied by the salt. So we come back to our original question. Our original question here is asking us that from the data, calculate the density of the salt. So to find the density of the salt, remember, like we said here, let me repeat it here. The density of the salt is given by mass of the salt divided by that volume occupied by the salt. And the mass of the salt, remember, we already knew the mass of the salt. According to our question, we're able to get the mass of the salt as 25 grams, which is right there. So the mass of the salt is 25 grams. Divide that by the volume of the salt, which is 12.5 centimeters cubed. And of course, this is going to give us 2 grams per centimeters cubed. So that is the density of the salt. A solid weighs 0.9 newtons in air and 0.2 newtons in a liquid of density 700 kilograms per meters cubed, or 0.7 grams per cc. Calculate the upthrust. That is straightforward. If I'm to draw here, this is a solid. It's dangling in air. Its weight in air is 0.9 newtons. Then when I put this in a liquid right there, its weight in the liquid is 0.2 newtons. So here it was 0.9, then it reduced to 0.2 because there was an opposing force that reduced that weight we call upthrust. Upthrust is an upward force. The downward force here is the weight of the fluid in air, and then of course this is the apparent weight in the liquid. This is the weight when the thing is in the liquid. Of course, for us to have gotten this weight in, the apparent weight in the liquid, which we are calling weight in the liquid, the apparent weight when the thing is in the liquid, it was weight in when the thing was in air, which is the downward force, minus the opposing force, the one that is responsible for this to reduce. So it's the weight in air minus the upthrust force. And of course, we know that the weight in the liquid is going to be 0.2, is going to be equal to the weight in air, which is 0.9 minus upthrust. We are interested in the upthrust. So upthrust is going to be 0.9 minus 0.2, and we shall end up with our upthrust being. So the upthrust force is 0.7 newtons. So Roman 2, they ask us to find the volume of the solid. Of course, we use Archimedes principle here. Volume of the solid, we shall say that the upthrust that we found Upthrust is given by weight of the fluid displaced. The upthrust here is 0.7 newtons, is going to be the weight of the fluid displaced, which is the mass of the fluid. Multiply that by gravity. What are we interested in? Remember, the question wants us to find the volume of the solid. So definitely this is going to be a density of the fluid. Multiply that by the volume of the fluid. Multiply that by gravity. Now the question wants us to find the volume of the fluid. The volume of the fluid is the same as the volume of the solid, since this solid, was immersed in the liquid. So this is going to be 0.7 newtons. So still 0.7 is given by the density of the fluid. What is the density of the fluid? They're telling us that the fluid is of density 700 kilograms per meters cubed, or 0.7 grams per cc. Now from here, I think we should use 0.7, 700 kilograms per meters cubed. So the density here is 700 kilograms per meters cubed. Multiply that by the volume of the fluid which we are looking for. Multiply that by gravity, which is 10 meters per second. And so when we say volume of the fluid, it's going to be equal to 0.7. Divide that by 700. Multiply that by 10. And that is what we get. And finally, we have this here, a block of material of volume 20 centimeters cubed and density 2.5 grams per centimeters cubed is suspended from a spring balance with half of its volume of the block immersed in water. What's the reading of the spring balance? Again, let's try to do this. It's a block of material. This is the block.